Roulette has no memory, the wheel does not know what it did last spin. Craps has no memory, neither do slots. Every game on that floor is a sequence of independent trials, and independence is the house's real security system. Not the odds, the independence. Blackjack is dealt from a finite shoe without replacement, which means it remembers. And in 1961, a mathematician at MIT proved that this one structural detail was enough to break the casino. Start where it started. In 1601, Cervantes wrote a story about two card sharps in Seville and described a game called Veintiuna. 21. The ace counts 1 or 11 and you must not go over. That is the oldest surviving description of the rule that still runs the table. It moved north as Veintiuna crossed the Atlantic and arrived in America unloved. So the houses bribed people in. 10 to 1 they said if your first two cards are an ace and a blackjack. The bonus died. The nickname did not. Nevada legalized gambling in 1931, and for the next 25 years nobody knew how to play the game correctly. There was folklore and there were books by card experts, and all of it was wrong by 2 or 3% a hand. Here is the whole game: 2 cards to you, 2 to the dealer, one of hers face up. Face cards count 10 and ace counts 11 or 1, and you want to beat her total without passing 21. A 2-card 21 is a natural. It pays 3 to 2. Your options are hit, stand, double for exactly 1 card, or split a pair. 4 verbs. The dealer has none. She is not a player, she is an algorithm. Draw until you reach 17, then stop. No judgment, no choices, which is the most important fact in the game because an algorithm can be solved. So solve her. Fix the up card. Her hand is a Markov chain with 6 absorbing states, 17 through 21, and bust. Recurse backwards and her exact outcome distribution falls out. And out falls the most useful table in gambling: dealer bust probability by up card. 2 35%, 3 38, 4 40, 5 43, 6 42, then 7 and it drops off a cliff: 26, 10 21, ace 12. That cliff between 6 and 7 is the spine of every strategy chart ever printed. Your side is harder because you have choices. Every position is a state: your total, soft or hard, her up card. The value of a state is the best of your 4 verbs, and hitting throws you into another state whose value you also need. That is a Bellman equation. In 1956, 4 mathematicians at the Aberdeen Proving Ground solved it on desk calculators over 3 years of evenings. Their abstract contains one of my favorite sentences in applied mathematics: the optimum strategy differs substantially from the published strategies of card experts. So basic strategy is not advice. It is the optimal policy of a solved Markov decision process, and it takes 3% down to 0.6, which is still negative. Play perfectly forever and you still lose. It is a floor, not a door. So where is the door? Thorp's paper opens with a question nobody had asked properly: whether the standard gambling games, which are not repeated independent trials, admit strategies favorable to the player. He is not asking about blackjack, he is asking about a category. Here is the object he saw. Forget cards. A shoe is a vector of 10 integers. How many 2s are left, how many 3s, up to how many 10 values, how many aces. 6 decks starts at 24 of each rank and 96 10 values, because 10, jack, queen and king are the same card to this game. Every deal decrements 1 coordinate and it never comes back up until the shuffle. And here is the move: your expected value is not a number, it is a function on that lattice. Basic strategy solves it at 1 point, the full shoe, and gets minus 0.5%, but the game spends almost none of its life at that point. So do what you do to any function you cannot evaluate everywhere. Take the gradient. Remove 1 card of a given rank, recompute the exact expectation, record the change. 10 numbers, they are called the effects of removal, and they are the whole secret. In a single deck, pull a 5, your expectation rises 2/3 of a percentage point. Pull an ace, it drops 6/10. 8s do nothing at all, and one more thing, the thing that makes it usable. Over the range the deck actually visits, the function is very nearly linear. The first order term dominates, which means you do not need the composition vector, you only need its projection onto the gradient. So compress, give every rank an integer: 2 through 6 plus 1, 7, 8, 9, 0, 10s and aces minus 1, add them up as they come out. That is high-low, and it is what everyone means by card counting. But look at what you just did. You took a 10-dimensional state vector and projected it onto a single integer axis. So whether a counting system is any good is not a question about memory or discipline. It is a question about angle. That angle has a name: betting correlation, the correlation between your integer tags and the real effects of removal. High-low, this crude thing you can teach a stranger in 4 minutes, scores 0.967. 97% of the available signal out of a vector of +1s, -1s and 0s. That is the actual miracle here, and almost nobody says it out loud. One correction? +6 means something very different with 5 decks left than with 1 because the effects of removal scale inversely with the cards that remain. So divide. Running count over decks remaining, that is the true count. And now the payoff? In a 6-deck game, your expectation is, to a very good approximation, a straight line, minus a 0.5% plus a 0.5% per point of true count. Break even at +1. At +6 you are playing with a 2.5% edge and you are the house. Which raises the only question that matters. How often does that actually happen? And here Blackjack gets genuinely beautiful because the running count is not a free random walk. High-low is balanced, the tags sum to 0 over a full shoe, so the count starts at 0 and it is forced to end at 0. It is a bridge. Sampling without replacement taken to the continuum is a Brownian bridge. The variance of a bridge goes like n times n minus n, pinned tight at both ends, loosest in the middle. But you do not bet the running count. You bet the true count, and dividing by the cards that remain does something violent to that. Put them together and the n minus n cancels once. The variance of the true count goes like n over n minus n. It does not peak in the middle, it diverges at the cut card. All of the extreme counts, all of the money lives in the last cards before the shuffle. Numbers, 6 decks, 312 cards. Cut the shoe in half, 3 decks left. The standard deviation of the true count is 2.6. Cut it at 3/4, a deck and a half left, it is 4.5. And a true count of +6 goes from 1 hand in 100 to 9 hands in 100. Same rules, same decks, same strategy. 1 inch of plastic moved and the frequency of your profitable hands changed by a factor of 9. Card counting is not a memory trick. Card counting is a bet on the tail of a Brownian bridge, and the dealer decides where you stop reading. One piece of honesty the movies leave out. In a good shoe your edge is about 1% of your bet, and the standard deviation of a single hand is 115% of it. Hands needed before your expectation merely equals 1 standard deviation, variance over edge squared. 13,160 hours of flawless play to reach a point where you are still a 1 in 6 chance of being down. Thorp gave people an edge, he could not give them a short run. So the casinos lost. Beat the Dealer came out in 1962 and became a bestseller, and in April 1964 Las Vegas changed the rules to kill counting. Business collapsed in 2 weeks, they changed them back, then they got smarter. New Jersey's Supreme Court ruled in 1982 that a casino cannot throw you out for counting. So nobody argues about counting anymore. They make the mathematics stop working instead. 3 ways. Penetration, cut the shoe earlier and you already know what that does to the variance. Payout, pay a natural 6-5 instead of 3-2 and you have added 1.39% of house edge, a flat constant and no bet spread recovers it. And the continuous shuffler, every hand the played cards go straight back in. Look at what that last one actually does, it is not a countermeasure, it is a proof. A continuous shuffler makes every hand independent of the last, it removes the state vector, it sets the gradient to 0, it takes the one game on that floor that had a memory and makes it memoryless like roulette, like craps, like everything else. They never beat Thorp, they deleted the variable he solved for. And look at the modern table, the main game squeezed to the bone, ringed with side bets at 3 to 8%. The beatable game got fenced off. The unbeatable one got a light-up sign, so what is Blackjack now? Mostly a memorial. Somewhere in that pit there is still a hand dealt double deck, cut deep, paying 3-2, and in that game the mathematics works exactly as it did in 1961. Everywhere else the game has been quietly edited until the thing that made it interesting is gone. Thorp did not find a way to beat Blackjack. He found out what Blackjack was, that turned out to be the more expensive discovery. Last time a margin call turned out to be a phase transition in a fixed point equation. It is on screen now. Subscribe and I will keep making the invisible structure visible.